So here's another example now of a projectile, but with linear drag. Okay, so previously we looked at projectile with no drag, just a classic projectile problem. But now let's say that there is some resistance due to the fluid through which the ball is traveling. But we assume what's called linear drag. Okay, let me read out the problem. A ball is thrown up at some angle in the xy plane. So we are ignoring z, which is perpendicular to the plane. We are just observing the ball moving in the xy plane, and y is the vertical direction. The acceleration is given by the equation. So this is given to you. A equals minus gj. Okay, j is the vertical direction, and the acceleration in the vertical direction has a component due to gravity, a minus gj. So that's acceleration in the downward direction with gravity g. Acceleration due to gravity g, and then there is another term which is proportional to the velocity with which the ball is traveling, and it's directed in the direction sort of opposite the velocity, so that's the negative sign, and there's a proportionality constant here. And this is the drag term. This would be called a linear drag term. In reality, probably if you threw a ball up in the air, probably that kind of drag that the ball experiences would be better approximated by quadratic drag. But for simplicity, we do linear drag. It turns out that if you do quadratic drag, we have to use a computer to actually solve the equations that arises. It's just a minor change, but that minor change makes it so that you cannot do a pencil and paper calculation. Or at least it's hard. Okay, so this is the acceleration term, and then our acceleration expression, and you're told that you're given the initial position, initial velocity, and you're asked to determine the velocity as a function of time in the x and y directions, and then the position as a function of time in the x and y directions. Okay, so that's the premise of the problem. We are given a vector equation for A, like we said, minus gj minus cv. What we can do is actually get scalar equations for the components ax and ay. Okay, so we don't really know how to integrate this directly, but if we can get ax equals blah, ay equals blah, we can integrate those scalars. Okay, so that's what we need to do. To do that, basically we need to replace a with ax plus ay, axi plus ayj, and then we need to replace v with vxi plus vyj. Like we said, the motion is only in 2D, so there is no motion in the z direction. So we are just focusing on I and j and no k. Okay. So we plug those things into this equation, we get this equation. And what we can do is collect all the I terms and the j terms. So on the right hand side, the I term is just vx. Oops, I suppose there is a math error here. So it's going to be minus c vxi plus vyj is what we have here, minus cv. So what I'm going to do here is combine this j term with this j term so that we have minus c vxi minus cg plus the minus minus gj minus cvyj. Okay, so that's what we have, which we can replace or represent as cvxi plus minus g minus cvyj. Okay, axi plus ayj equals these two quantities. Okay. When you have a vector equation like this, you have a bunch of I and j terms here, you have a bunch of I and j terms here. By necessity, the I term here should equal I term here, the j term here should equal the j term here, okay? In other words, the component along the I direction of this vector should be the same as the component of this vector along the I direction. And only then will this vector equal this vector. So that's a basic principle of vector math, arithmetic, whatever you want to call it, well, vector algebra. So what we have, so equating the I terms. So this is something you will be doing over and over again throughout the course, basically equating like terms. We get this equation, and then equating the j terms. We get this equation. Okay, so these are equations. These are now the scalar equations that we can now try to integrate. Okay, so we have acceleration along the x direction is now a function not of time but velocity in the x direction. Similarly, we have the acceleration in the y direction, which is a function of not time but velocity in the y direction. So we need to now use the kinds of tricks that we learned last lecture to integrate when you have acceleration as a function of velocity. Okay. Note the accelerations are known as functions of velocity. Okay, so but thankfully we don't have any mixing between the x and the y direction. The x acceleration depends only on the x velocity. The y acceleration depends only on the y velocity. If the y velocity, y acceleration depended on the y velocity as well as the x velocity, things become more complicated, and you may not be able to use pencil and paper to actually solve for things analytically. May not be, but you will always be able to solve it using a computer. Okay, but thankfully in this particular case you can consider the x separately and y separately. So let's do that. Let's do the x direction analysis, and we have, just to recap, ax equals minus cvx. Ax is of course dvx by dt. I'm just sort of recapping what we did last lecture, and we can there's v here, there's t here, there's v here. We bring the like terms together, all the velocity terms to one side and all the time terms to the other side. So we have that. We can integrate both sides with respect to whatever we are integrating with respect to. In this side, we are integrating with respect to velocity, and on the right-hand side, we are integrating with respect to time. So we put that there. Integral of dv over v, what is that? So we sort of saw this last time. It is going to be equal to the log vx, and then we can apply the limits. And then the right hand side is pretty simple. It's just t, integral dt is just t, and we can apply the limits like so. Here, just plugging things in. This is vx minus log vx naught. This is c t minus t naught. Let's, for simplicity, assume that t naught is equal to 0. The initial time is 0, so that we are not carrying t naught around. But it doesn't matter. Say t naught equal to 0. let's say it's given. Okay, let's say that's given. Then we just have, this is minus CT. I'm just going to simplify the expressions a little bit. On the left-hand side, we have log something minus log something. And that's a formula that says that log A minus log B is log of A by B. So that's what we get there. Now we have time in some sense as a function of the velocity. How do you get velocity as a function of time? We got to remove the log. Just like last time, we can do an exponentiation to get rid of the log. So we exponentiate both sides. And e power log whatever p equals p. Okay, so basically we have Vx over Vx naught, which is basically e power log Vx over Vx naught equals e power minus Ct. So essentially we have Vx, which is basically Vx of t, Vx naught e power minus Ct. Okay, so this is the function that we're looking for. This is the answer. Vx of t equals Vx naught e power minus Ct. Okay, so that's an answer. That's one of four things that we wanted to find. This is Vx of t. Okay, we can do a sort of go through almost the same procedure. We can find Vy of t. The expressions are going to be a bit more complicated, but not too complicated. In fact, the Vy of t is quite similar to the problem that we solved last time. Motion in a straight line. In fact, it's the exact same thing. Okay, once you have Vx of t, what do? To get position, x of t, we just go x of t equals x naught plus integral. This is now a function of time, so it's just integral v of t. We can do t naught, but we just set t naught as 0, so it's just that. So we can do the integral directly. Vx naught e power minus Ct dt. Let me just do the integration carefully so we can bring the Vx naught outside. We can do that. Integral e power minus Ct is just integral e power minus Ct divided by minus c. Okay. And then we can plug in 0 one time, t. So again, you want to be able to do these integrals. Of course, given the nature of the exams, you will have access to integration tables and things like that, but you should be comfortable using them or knowing these basic integrals, okay? Okay, so we can plug those things in. Let's do that. X naught plus Vx naught. Let's plug in t, which just gives us exactly the same thing. And then let's plug in 0. E power 0 is 1. So we have okay, so moving along, x of t equals x naught plus or we can bring the minus c outside. So we can do Vx naught divided by c e power minus ct minus 1. Okay. And that's it for the x motion. We've gotten the velocity in the x direction, as well as the position in the x direction. We can follow essentially the same procedure to do velocity in the y direction and the position in the y direction. I will post notes for that, but you should also try to do that on your own. Okay, like I said, it's quite identical to the problem that we did in the first lecture. The integrals reduced to exactly the same things. Okay, so that's the end of this little piece.